Hey there, AP Chem scholars. Sorry, I have to shift things around again. I'm going to be out at a funeral today. So we're going to keep going with Chapter 8. We'll do a little bit of review stuff tomorrow. The test on Chapter 7, or Unit 7, whatever you want to call it, is going to be a take-home thing. Okay? I just can't take the time anymore. I can't keep moving things around. But we'll talk more about that when I am in school with you tomorrow. In any event, I'm going to continue our discussion about weak acids, weak bases. I know I started talking about polyprotic acids a little bit the other day, so I want to pick up on that idea. Again, prot is from proton because of the hydrogen ion, which is essentially a proton. Okay, so H2SO4 is polyprotic technically, but one of the things we are talking about is that the pH really only depends on the first hydrogen. And I'm going to try and show you that here now, although realistically we could go through and calculate out other things as well. So we know that, when we talk about sulfuric acid, this is really not a reversible reaction, okay? Because it's such a strong acid, it really goes one way. Okay, the Ka for this, if we treat it as equilibrium, it'd be too large to be defined. So we don't really need to look at that as equilibrium. So, if I had a concentration of sulfuric acid, let's say 1 molar, I know that the hydronium would be 1 molar. Okay, now let's talk about what happens next then. So we form this bisulfate ion, HSO4 minus, and that in turn could, in theory, give a hydrogen. Lost my spacing there. Do that. All right. And it turns out the Ka4 bisulfate is something like 0.012, which is not all that low, but obviously less than 1. So let's talk about what goes on there. So, all right, so I had said 1 molar. Let's say it's a 2 molar solution. Okay. So again, in this case, we could look at this as a one-directional reaction. Okay, so the hydronium, wow, I'm just all over the place here, aren't I, guys? Sorry, it's just been that kind of a day. Anyway, we'll just leave it there for a minute. Is 2 molar, and the bisulfate is also 2 molar. Okay, so now let's look at the second reaction. So we have the bisulfate ion plus water, making hydronium and sulfate. Okay, but we got to remember that from the first reaction, we know that the bisulfate is 2 molar, and we know that we have hydronium that is 2 molar. So the bisulfate is going down by x, the hydronium is going up by x, the sulfate is going up by x. So we would have 2 minus x, 2 plus x, and x. Now we know, since it's a weak acid, we can assume 2 minus x is pretty much 2. 2 plus x is pretty much 2. If the minus x is too small to matter, then the plus x is too small to matter. So we have really 2, 2, and x. Okay, so we can simplify this down. But let's do it the long way anyway, just to prove the point. So 2 plus x times x over 2 minus x, I FOIL it, well, not so much FOIL it, but kind of. I distribute my x's here. That's where I got 2x plus x squared. I cross multiplied 2 minus x times 0.012. That's where I got 0.024x minus 0.012x. Then I brought it all together. X squared plus 2.012 minus 0.024 equals 0. I get two answers. One is negative, the other is positive. So the hydronium then was 2 plus x, we had said, which is 2 plus 0.0119. Well, that's still pretty close to 2. So we did that extra math. Didn't really need to. If we had just assumed the hydronium was 2, we would have gotten a pH of negative 0.301. If we do out the calculation and use 2.0119, the pH is negative 0.303. Not a huge difference. But the point is, we really didn't need to go through that whole extra step then. If we had just assumed right from the start that hydronium was 2, like it was from here, there was no reason to really go through and calculate it all out, okay? So the point being, the first ionization is really the only significant ionization. Okay, so we end up basically right where we were. And again, this Ka value for a weak acid is really kind of big. Most Ka values are 10 to the -5th, 7th, 9th, 13th, etc. Much, much smaller numbers. So it becomes even more negligible. Okay, so anytime you're asked about the pH of any polyprotic acid, you just look at the first ionization and that's it. Okay, it doesn't matter whether it's a weak or strong acid. If it's a weak acid, obviously you're still going to have to calculate it out from Ka, but the point is you only need to do it for the first ionization. Okay, speaking of ionization, we talked about percent ionization already. So again, I'm reviewing this. I know we did this question. We talked about 0.5 molar HCN. We found that hydronium was 1.57 times 10 to the -5th. If I take 1.57 times 10 to the -5th, divide by 0.5, I get a very tiny percentage. Okay, so again, that just emphasizes the weak acid thing. All review, I know. I know we also talked about weak bases up to the bell a little bit, so I want to make sure we're okay with that. When we're talking about a weak base, again, there's not ionic compounds for the most part. Okay, we're really not going to see most bases other than the 8 strong bases. We're not going to see bases that are ionic. So I just put a generic term Q here plus H2O, and the H2O is going to be the acid, Q is going to be the base. That means we're going to end up with some cation of HQ plus and the hydroxide ion, and our Kb will take the format of this cation times hydroxide divided by Q. Really same idea. So let's talk about ammonia. Okay, if I take ammonia plus water, I would get ammonium plus hydroxide. My Kb would be ammonium times hydroxide divided by ammonia. So what if we had 2 molar ammonia and Kb was 1.8 times 10 to the -5th? Well, all right, we already set up our expression. Okay, so we have to recognize that we're starting with 0. We're going to end with x on both of these. This would be 2 minus x, but again, 2 minus x, we get simplified down to just 2. Notice I didn't do the whole ICE table. If you want me to backtrack and explain it, I will. So I would multiply both sides by 2, then take the square root, and I find that x, or my hydroxide, is 0.0060 molars, which means then that my POH is 2.22, which means that the pH would be 11.8. Now we're going to roll that right into what was kind of supposed to be covered in the last unit, and I'm still wrapping my head around why they wanted this to be in Unit 7, talking about the pH of salts. Now we're going to do it descriptively and quantitatively, so keep that in mind. When we talk about salts, we are talking about ionic compounds now, okay? So that, where the acids we said really aren't and bases mostly aren't, okay, salts are ionic compounds, end of story, okay? But, we talked about in the Bronsted definition that, an anion being negatively charged is going to be good at attracting protons, so that means it's a good base. So ions actually do factor into pH as well, and we're going to get into that idea. Now, there's a set of rules about this that I think is painful. I'm not even going to go into this. I think there's a much easier way to talk about it than all this. So why did I list it? Okay, because this is, kind of like the whole AP view of it. So by all means, if you want to copy this down, pause the video and go through it, that's fine. But there is a simpler way to talk about the strength of the pH, the relative pH of a salt. Okay, so actually let me go right to that. Okay, one of the examples there was sodium hydrogen phosphate. Okay, and we want to know if the salt is acidic, basic, or neutral. So what we do, just like with the weak acids, just like with the weak bases, we add water to it. So I want to neutralize, I want to try and write out a double replacement reaction here. Since there are 2 sodiums, okay, I'm going to use 2 waters, okay, so that I get 2 sodium hydroxides, and now the HPO4 becomes H3PO4 over here, okay. So that is my double replacement reaction. Now I look at this and I see that H3PO4 is a weak acid, NaOH is a strong base. Well, That means the base is stronger than the acid, which means that the solution has to be basic. So we can kind of, just by looking at a hydrolysis or a reaction with water, it's much easier to assess whether something is an acidic salt, a basic salt, or a neutral salt. All right, so think about these reactions real quick. Silver nitrate plus water, sodium chloride plus water, calcium fluoride plus water, and tell me which one is acidic, basic, or neutral. Pause it. I'm going on. So silver nitrate plus water gives us silver hydroxide, a weak base, and nitric acid, a strong acid, which means that this is an acidic salt because we're getting a strong acid versus a weak base. Sodium chloride plus water gives us sodium hydroxide, a strong base, and HCl, a strong acid. That's equal in strength, so this is a neutral salt. Calcium fluoride plus water gives me calcium hydroxide, a strong base, and hydrofluoric acid, a weak acid. So now the base is stronger than the acid. This is a basic salt. So from that point of view, it's real easy to assess the salts part. But let's talk about trying to put a pH to these now. So if we want to find the pH of a salt, we need, when it was a weak acid, we needed Ka. When it's a weak base, we need Kb. What do we do for a salt? Well, we need either Ka or Kb, depending, I guess, on whether we want to say it's an acidic salt or a basic salt. And yeah, I'm sorry. Of course, if it is neutral, we can pretty reasonably assume that it is a pH of 7. So let's look at a couple reactions here involving water. So ammonium plus water would give us a reaction of hydronium plus ammonia. Ammonia, a base, plus water would give us hydroxide plus ammonium. If I were to add these two reactions up, I get our water reaction. Two waters yield hydronium plus hydroxide. Well, let's think about KEQ and what we learned in the previous unit. When we add up reactions, we multiply the K values. Well, the first reaction is a Ka reaction, right? Because we're talking about making hydronium. It's an acidic reaction. The second reaction is a basic reaction. We're getting hydroxide, but the last reaction is water. So we have Ka, Kb, and Kw, but when we add reactions, we multiply the expression. So that means that Ka times Kb equals Kw. For any conjugate pair, Ka times Kb equals Kw. What do I mean by conjugate pair? Again, ammonium and ammonia are a conjugate pair. We see them here, we see them here together. Okay, here it's an acid and the conjugate base. Here it's a base and the conjugate acid. That's what we mean by conjugate pairs. Okay, now, some people like to talk about pKa, pKb, pKw. Okay, so pKa. The P we've been doing all along is per, right? But that's really what's indicating the logarithm thing. So for pH, we did negative log of hydronium. For pOH, we did negative log of hydroxide. For pKa, we do negative log of Ka. For pKb, we do negative log of Kb. For pKw, we do negative log of Kw. Well, Kw at room temperature, we know is 1 times 10 negative 14, which is Ka times Kb. So that means that 14 equals pKa plus pKb. So if you were given the pKa value, you could find pKb very easily by subtracting, or if you were given the Ka value, you could find Kb by dividing. So either way, we have a situation where we can find the K for a conjugate by knowing the other pair, part of the pair. Okay, let me explain what I mean by that. So let's say I have a solution of sodium fluoride. All right, so sodium fluoride is a salt. Okay, when we react it with water, sodium is a spectator ion. Okay, so we end up with the net reaction of fluoride plus water makes HF plus OH. So clearly this is a basic reaction. I see the hydroxide ions here. That means I need to know what Kb is. However, I can look on a table and find that HF has a Ka value of 6.8 times 10 to the negative fourth. And since I know Kw is 1 times 10 to the negative 14th equals Ka times Kb. I can take my 1 times 10 to the negative 14th, divide by Ka, 6.8 times 10 to the negative 4th, to find that Kb for this reaction is 1.5 times 10 to the negative 11th. Now that I know the value of Kb, it's just like that other problem we did before, finding the pH of a weak base. So I set up my ice table. Okay, I have the 1 minus x here, but I'm going to treat that just as 1. My Kb we just found to be 1.5 times 10 to the negative 11th. So now I just multiply by 1, take the square root. My hydroxide is 3.87 times 10 to the negative 6 molars. And this is in my way. Come on. Oh well, you'll have to bear with me. Anyway, which means the pOH is 5.41 and the pH is 8.59. So finding the pH for a salt is very doable once you do that little adjustment for the conjugate. Okay, so that's where I'm going to wrap up for now. I encourage you to work on your practice problems or the AP classroom assignment, but that's where it ends today. All right, have a good day, guys. I'll see you tomorrow.